Hello everyone. Today I'm going to present our work that has been accepted at WACV 2024 entitled Source-guided Similarity Preservation for Online Personal Identification. This is a joint work done with Jhony Giraldo and Stéphane Lathuilière from Telecom Paris and Nicolas Winckler from Athos. We first start by introducing the problem we want to solve and its main challenges. Personal identification is the task of identifying a person of interest. The goal is to determine whether this person has appeared in another place at a distinct time, captured by a different camera, or even the same camera at a different time instance. This comes with many challenges that are, but not limited to, variation in the illuminations, pose variation, occlusions, or having different identities with similar appearances. Therefore, the community that focuses on this problem tries to develop methods that can produce robust future representations to those challenges. In this work, we propose to follow the challenging yet practical setting, the OUDA read, which is the online unsupervised domain adaptation for personal identification. First, this setting consists of having the two main assumptions of the OUDA, that are having access to a well-annotated source domain dataset and also having access to an unlabeled target domain dataset. In contrary to the classical OUDA setting, in OUDA we have the following constraints. First, online adaptation. So when deploying a personal ID system, we gather images as long as they are recorded under the form of a stream that continuously provides images from different cameras or places. Therefore, the target domain dataset is not accessible all at once, but in a stream fashion where only small batches of images are available at a given instant of time. Second, since the re-ID task involves personal identities, the system is confronted to confidentiality purposes in many countries, forcing the technology provider of such models to discard previously seen images, which brings us to the second constraint of privacy protection, where images captured by the different cameras are stored for only a limited period of time. Finally, the aim of this challenging setting is to enable personal ID models to be continuously updated while also improving the adaptivity to changes in the target domain. The OUDA setting comes with two main challenges that need to be addressed. First, catastrophic forgetting that appears naturally in continuous settings where the model only observes a few target identities per task, and consequently the model tends to forget previously learned identities. And the second is domain shift, which is the change in distribution between the source and target domains. Now, we discuss the motivation of our work and the proposed method. We conducted some preliminary experiments showing that using a memory bank that stores images from the past and previous target tasks improves significantly the performance of re-identification, since it helps the model refresh its memory and keep all the acquired knowledge. However, this kind of methods, also known as replay-based methods, do not align with the OUDA privacy constraints. So how can we estimate the distribution of previously seen images without the need of storing them? The answer will come with our framework, Source-guided Similarity Preservation, or S2P, that will be presented in the following slides. So the S2P framework consists of source-guided knowledge distillation module. This will ensure that the previously acquired knowledge is preserved during the continued learning. To this end, as shown on the right-hand side figure, we employ a teacher model that will progressively distill the knowledge to the student model, where the distillation is performed in the future space over a set of source-based support images. Concerning the support set, it contains, as shown in the left-hand side figure, images from the source domain that are similar to previously seen images or tasks. This solution encourages the student model to project the images into a common future space, resulting in a more discriminant and task-invariant representations. The second module is the source-target distribution alignment. Here, we propose to use the maximum mean discrepancy with a Gaussian kernel to explicitly reduce the domain shift between the source domain and the target domain. We also propose to utilize the teacher model in the computation of the MMD loss. In fact, we minimize this loss between the target futures computed by the student model, B, and the source futures computed by the teacher model, B bar. Finally, the figure shows the overall pipeline of the S2P framework. We follow the common training scheme that was adopted by almost all pseudo-labeling-based methods. First, the student model is pre-trained on the source domain dataset, then it is fine-tuned on the unlabeled target dataset using the different loss functions presented before. First, we have the KD loss, which is a loss optimized to preserve the previously acquired knowledge during the continued learning. MMD loss, which is the maximum mean discrepancy loss to explicitly minimize and reduce the domain shift between the target and the source domains. And finally, the re-ID loss that corresponds to the re-identification loss of the integrated UDA method. So as you can see by construction, the S2P framework can incorporate almost any UDA method in order to adapt it to the OUDA setting. Now we move to the experiments part and the main results. We evaluate the S2P framework for the OUDA setting in several real-to-real and synthetic-to-real adaptation scenarios. For each configuration, we split randomly and uniformly the target dataset into 5 subsets corresponding to the 5 tasks of OUDA setting. For each configuration and for each method, we report both the mean average precision and the CMC rank 1 accuracies. It can be stated from the table that S2P significantly improves the performance of the state-of-the-art methods in all the configurations. We also conducted additional experiments to assess the effectiveness of the two main losses of our S2P framework, that are MMD and KD losses. It can be shown from the first table on the left-hand side that integrating either MMD or KD losses significantly improves the performance in all the configurations. Furthermore, combining both losses leads to an additional overall improvement in performance in all cases. The second ablation study delves into our knowledge distillation mechanism, focusing on two main factors: the choice of the KD loss function and also the choice of the selection strategy of the support set. We compare in the first part of the second table our method against two different strategies of selection, where it can be shown that our similarity-based selection strategy is best suited to the OUDA read. Moreover, our knowledge distillation loss also gives the best results compared to other knowledge distillation losses. Finally, in the figure on the right-hand side, we show some random samples of the support set in two different configurations, real-to-real and synthetic-to-real. And it can be shown that qualitatively, our selection-based method selects only images that are similar in both appearance and pose of identities from the source domain. To conclude, we have presented our S2P framework that jointly addresses catastrophic forgetting and domain shift problems that are encountered in the OUDA read. This is mainly based on the KD mechanism that employs a support set that respects privacy regulations. The results on extensive experiments have shown that S2P manages to straightforwardly incorporate existing state-of-the-art unsupervised domain adaptation methods while also improving their performances. Thank you.